Hello. I wanted to add this short segment to session 10 to integrate two approaches to explaining what makes the rotor turn in a motor. And to do that, we're going to start with a quick review of our two left-hand rules. So I've got our first left-hand rule says if the electrons are moving up this wire, they produce a magnetic field of the fingers curled around. This is using our left hand. Our fingers curled around the wire tell us which way the magnetic field is going to go. Okay, first left-hand rule. Second left-hand rule tells us that if we got electrons moving toward me through a magnetic field, so they're moving toward me, the red thumb indicates they're moving toward me through a magnetic field which goes from north to south, that wire will experience a force upward. Second left-hand rule. Now let's apply these to the motor. Now, last time we looked at primarily two rotors. There was the commercial rotor that's in all of our hand power tools and some of our kitchen appliances and vacuum cleaners and all kinds of areas in our automobiles. And then we had a little homemade motor. So we're going to try to capture the essence of these two motors with the simplest possible configuration, and that is the single loop, where we're going to have this is going to be our commutator, where we put the electricity into this, and the electrons are going to travel down this wire and back this way. Okay? This is what we're going to do our analysis with. So here are the poles of a U-shaped magnet. This is what we're working with right here. Let's go out just a little bit. And so if I've got electrons moving in this loop, then our first left-hand rule says that there's a magnetic field going into the loop with the electrons moving in the direction of my red thumb there. Now on this side, they're going in the other direction, and again, the magnetic field is into the loop. Okay? So there's a magnetic field going that way. Now, in earlier sessions, we agreed that the magnetic field goes from north to south. Okay? That is the direction of the magnetic field, from north to south. So if it's going into something, that in thing is a south pole. And we agreed that this rule, the left-hand rule, is causing the magnetic field to go down. Okay? So what that means is we have a south pole up here and a north pole down below because the field's going to this in that direction. Now, if we're creating a south pole up here and a north pole down there, obviously the south pole is going to be repelled by the south poles of this magnet and be attracted by the north poles of this magnet. So it would want to turn that way. And we're going to remember that with this arrow down here. That's the direction the upper part of this thing, our rotor, wants to turn. Okay? That's the direction this wants to turn based on our first left-hand rule. Now, let's start over using the second left-hand rule. I have electrons, again, are moving in that direction in this wire. and the direction of the magnetic field is that way, indicated by the blue finger from north to south. And in that case, notice the black finger, which is the force finger, is pointing straight down. So this wire is experiencing a force downward. And then over here, the electrons are now moving this way in this wire. They're moving that way through a magnetic field that's in that direction from north to south, and the force is pointing upward. And again, it wants to rotate this way because the force on this wire is up, the force on this wire is down, wants to rotate that way, which is what the other model projected. So they both project, or they both determine that it's going to turn in that direction. So which one do we pick? Well, it kind of depends on whether this magnetic field is super strong or the one we create with a loop of wire is super strong. So to make that point, we're going to use these actual field magnets of a motor. And the reason for that is if I insert the rotor core into there, you'll see that there's hardly any air gap, which means what this core does is allow for there to be a let's leave off that magnetization of the core. What it does is it tells us we can produce a really strong magnetic field in here, and if there are wires in that, they are going to react to it. So I'm going to turn this way, and we'll look at it from the end. And let's put the core on here. Oops. We'll slip the core into our loop and get this in here. Okay, now we've got two ways of looking at this. If it's a super strong magnetic field from the field magnets, we have a horizontal magnetic field with electrons flowing in it. Then it's the Lorentz force that's going to drive it. This is going to want to turn. If, however, we have a lot of electrons moving through that coil, and this isn't a super strong magnetic field, then the way it's going to behave is I've got a north pole and a south pole interacting with another north pole and south pole, and that again is going to turn it. So it depends on what your situation is as to which approach you want to take, whether it's electrical currents in a strong magnetic field or two magnets, one an electromagnet and the other one can be a permanent or an electromagnet. It doesn't matter. So either way is valid. Just depends on your situation. So I hope that made it more, that explained how the two can work together. I hope it wasn't too confusing. In session 11, we're going to take a look at how we produce electricity itself from magnetism. Okay, thanks for coming. I'll see you next time.